Alright guys, this is video part 2 for looking at some sample AP Physics 2 questions dealing with Unit 4, electric circuits dealing with resistors and capacitors. So this is the 11th question out of a total of 19. So the first 10 are in video part 1, check it out, and this will be like the last 9. Question 11 reads, the figures above show two circuits with identical batteries, resistors, and capacitors. The circuits have reached a steady state. Which of the following is true about the charge Q on the capacitor plates to which the arrow points? So the first circuit, circuit W, has a capacitor just in series with a resistor. It's being charged by the battery until it reaches a steady state. And in the second circuit, essentially the same thing, except we now have an additional capacitor of the same capacitance that's hooked in parallel with this other capacitor, also hooked up with this resistor. So in both of these circuits, by the point these things reach a steady state, there's going to be no more current flowing out of the battery, no more current flowing to the battery. These guys will essentially be fully charged, and each capacitor in this circuit and each of them in these circuits will actually end up having the same voltage across the same voltage across the plates as the voltage of the battery. And so if we're trying to think about the amount of charge stored on them, on the capacitor plates, like we have to think about, well, they have the same capacitance, so how is the charge stored on capacitor plates related to the capacitance and the voltage across it? Well, go up to this AP Physics 2 equation that the voltage difference across capacitor plates is equal to the charge stored on the plates divided by the capacitance. Right? Or you can rearrange this equation for Q, since we're asked about the charge on the capacitor plates. We get Q is equal to capacitance times the change in voltage. And the problem statement said that all three of these capacitors, well, the two that the arrows are pointing to and this other one, have the same capacitance. And so the charge stored by each of those capacitors will vary as the change in voltage across the plates varies. But like I just said, there's going to be the full voltage of the battery across each capacitor here in parallel and across here. And so if the change in voltage is the same, if the capacitance is the same, that means the charge stored on this capacitor and this capacitor has to be identical. So the charge stored on the capacitor in circuit X is equal to the charge stored on the capacitor in circuit W. Number 12. A student has several conducting rods made from the same material. The rods have the same length but a different square cross-sectional area. The student places the rods in a circuit so they have the same potential difference across them and then measures the current in each of the conducting rods. Which of the following graphs most likely contains a best fit line to the graph of the current I as a function of the cross-sectional area A of the rods? So I didn't draw a circuit, but there's just basically a rod that's going to act like a resistor. They put a potential difference across it, and the question is, how is the current flowing through it change as a function of the cross-sectional area? So is current stay constant for different cross-sectional areas, or does it increase linearly, decrease linearly, or is it a hyperbolic relationship? Well, we kind of have to figure out how is I, current, going through a resistor, or in this case, a conducting rod, algebraically or graphically related to the cross-sectional area. Well, let's come down here. We kind of have to think about these two AP Physics equations. One is that the current going through anything is equal to the change in voltage across that thing divided by its resistance. And we're not given resistance directly, but they said it's the same material, so they will have the same resistivity. It's the same length, L, and surface area A, or not surface area, cross-sectional area A, and resistance of something is equal to the material's resistivity times its length in meters divided by its cross-sectional area in meters squared. So if we combine these two equations, plug in this expression for R, we get this. I is equal to delta V over resistivity times length divided by area, or if if we're taking delta V divided by resistivity times length divided by area, that brings the area up in the numerator and we get this. that current is equal to change in voltage divided by the resistivity times the length, all multiplied by area. And like these values, the problem statements that are the same voltage drop across each conducting rod, the same resistivity because they're the same material, and the same length. So these are all constants. And so we can see that current, if all of these other things are constant, like we said, is proportional to the cross-sectional area. So as area increases, current will increase, which makes sense because if the area goes up, the resistance goes down. If the resistance goes down, the current goes up. And it shows that we would expect to see a linear relationship. So if we double the cross-sectional area of the conducting rod or a wire, it's going to double a current. And so we would expect to see a linear trend between current and cross-sectional area. Question 13 reads, two parallel conducting plates are connected to a constant voltage source. The magnitude of the electric field between the plates is 2,000 newtons per coulomb. If the voltage is doubled and the distance between the plates is reduced to 1/5 the original distance, the magnitude of the new electric field is what? So remember, with capacitor plates, if we connect two parallel conducting plates to a battery, the one that's connected to the positive side of the battery will have a net positive charge. The one connected to the negative side of the battery will have a net negative charge. And there's going to be a uniform electric field between those two plates. So it's going to be the same strength all throughout, from the positive side to the negative side. And the original electric field strength for a given battery voltage and a given separation distance, let's call that delta R, is 2,000 newtons per coulomb. If we double the voltage of the battery, but we bring these plates closer together, the question is, what happens to the strength of this uniform electric field? Well, rather than looking at the equation for, let's say, the electric field created by a capacitor, since we're just talking about the relationship between the electric field and the change in voltage between 2 points and the distance between those 2 points we call delta R, we just have to use this equation. This tells us how the electric field is related to voltage and distance. So, if E is equal to delta V over R, do a little proportional reasoning. If we're doubling the original voltage, so there's a 2 in the numerator, and we're like taking the original separation distance and making that 1/5 the original distance, it's 1/5 the original separation distance, delta R0. And so 2 divided by 1/5 is just 10. And so doubling voltage, dividing the original distance by 5, changes the right side of this equation by a factor of 10, which means it would change the left side of the equation, which is the strength of the electric field, also by a factor of 10. So the new electric field strength, call that E2, is equal to 10 times what the original electric field strength was. The original electric field strength was 2,000 newtons per coulomb. 2,000 newtons per coulomb. So multiply that by 10 and we get a new electric field strength of 20,000 newtons per coulomb. So our answer is going to be E. Question 14 reads, two parallel conducting plates separated by a distance d are connected to a battery of EMF E. Which of the following is correct if the plate separation is doubled while the battery remains connected? So if the battery remains connected to our parallel plate capacitor, that means the voltage across the plates has to stay the same. So the question is, what is correct? So if the battery is connected and the voltage stays the same, that means automatically choices C and D, which says the potential difference between the plates is either doubled or halved, can't be true because if the battery remains connected, the voltage is constant. So here's our situation. We've got a battery connected to parallel plate capacitor separated by some distance. We're basically doubling the separation distance right here, so it's farther. And the question is, what's going on? Well, the capacitance is unchanged. Turns out that's not true because capacitance depends on surface area and separation distance, so the capacitance is changed. So the only other two choices talk about what's going on with the electric charge stored on those plates. And either the charge stored on the plates is doubled or it's halved. It goes up or it goes down. So how do we think about what is the relationship between the charge stored in the plates, that's Q, and the separation distance of a capacitor? Well, we've got these two AP equations that we worked with this one in the last problem. We also have to kind of bring in this one, which tells us the electric field created by a capacitor or between capacitor plates. If we know Q, the charge stored on the plate, on one of the plates, divided by epsilon naught times the surface area of those plates. So this would tell us how big the electric field is if we knew charge and area. And we could also use this equation for capacitors where the electric field is related to the change in voltage across the plates divided by the separation distance. And notice, in this equation we have charge, Q. In this equation we have the separation distance. And so we want to find out how these two variables are related to one another. And we have to do that through thinking about how each is affected or affects the strength of the electric field. So we can put this equation and set that equal to that because they're both equal to the electric field inside of a capacitor. So we get this. Charge divided by epsilon naught times the surface area is equal to the change in voltage across the plates divided by the separation distance. And since we're looking for how Q is related to delta R, I'm going to kind of like move delta R to the right out here, and then I'm going to move epsilon naught in area, multiply each side by that, so it moves over to the right hand side, and we get this, just rearrange a little bit algebraically, that Q is equal to epsilon naught times surface area times change in voltage across the plates, all of that multiplied by the inverse of the separation distance. And think about this, everything inside of the parentheses is the same for both situations, right? That's a constant. If you increase the separation distance, you're not changing the surface area of the plates. And since the battery is connected, the change in voltage from one plate to the other is also the same. All these guys are constant, which means here's our algebraic and graphical relationship between the charge in the plates and separation distance if everything else stays constant. So if we're doubling delta R, so twice delta R or twice the separation distance means the charge on each plate has to be halved. As R goes up, the charge stored in the plates Q goes down. And so the answer is B. The electric charge in the plates is halved. Okay, question 15 says, in the circuit shown above, the switch S is open, the capacitor is uncharged, and the current through the battery is 1/2 of an amp or 0.5 amps. Question is, what is the charge in the capacitor a long time after the switch is closed? So while the switch is open, there's just current flowing out of the battery. Can't go through this branch because the switch is open, so it's going to flow through the 10 ohm resistor, flow through the 5 ohm resistor back to the battery. So just get essentially a simple series circuit, 10 ohm and a 5 ohm in series. Well, what happens when we close this switch and this capacitor is initially uncharged? Well, when the switch is closed, you're going to get like some of the current that comes out of the battery will flow into the towards the capacitor and keep going around there. And that'll keep happening until the capacitor reaches equilibrium, until it's charged as much as it can be in this circuit configuration. Well, it says after a long time, what's going on? Well, after a long time, this capacitor will be charged as much as it can be. And a capacitor in equilibrium has no more current which flows to it or from it, which means this is going to act like a break in the circuit. Like, again, that's going to be like it's not even there. And so when this is fully charged, we essentially just get current in our simple series circuit, again, that flows through the 10 ohm and the 5 ohm. And if we want to know, I guess, the charge on the capacitor, we kind of need to know what the voltage is, like how much voltage difference is across those capacitor plates. Because, going to this equation, this tells us how much charge Q is on capacitor plates of a given capacitance, and if we know the change in voltage across it. Or if we solve this for Q, the charge in the plates is equal to the capacitance times the change in voltage across it. And if you look in the diagram, they gave us the capacitance. It's 5 microfarads. Micro is times 10 to the negative 6. So 5 microfarads is 5 times 10 to the negative 6 farads, and a farad is a coulomb per volt. So we know capital C. All we need to do is figure out the change in voltage across that capacitor. Well, that capacitor is essentially when this is charged and there's no current flowing here, current flowing here. If there's no current flowing through the 10 ohm resistor, there's no voltage drop across it, according to Ohm's law, which means like the voltage across the capacitor is the same as the voltage across this point and this point. And this branch is in parallel with this 10 ohm resistor. And if two things are in parallel, they have to have the same voltage across them, which means, you know, as 0.5 amps, again, goes through the 10 ohm and the 5 ohm, there's going to be some voltage drop across the 10 ohm resistor. And that's going to be the same as the voltage drop across this branch, which will be the voltage across the capacitor plates. So if we can just figure out the voltage drop across the 10 ohm resistor, that'll tell us the voltage drop across the capacitor plates, and we multiply by the capacitance, it'll give us the charge stored on that capacitor. So we know there's 0.5 amps of current which flow out of the battery and flow through the resistor, 10 ohm resistor. So if we want to figure out the change in voltage across the 10 ohm resistor, we take the current going through it multiplied by its resistance. So there's 0.5 amps going through it multiplied by resistance. That must mean there must be a 5 volt drop or a 5 volt difference in electric potential across that resistor. So it's got to drop by 5 volts. And if there's a 5 volt difference across the 10 ohm resistor, like we talked about, there also has to be that same 5 volts across the capacitor. So we can plug in 5 volts for the delta V here in this capacitor equation. So our capacitance, 5 microfarads, or 5 times 10 to the negative 6 coulombs per volt, multiplied by 5 volts. Notice the volt units cancel. And we end up getting that the charge stored on the capacitor is 2.5 times 10 to the negative 5th coulombs, or that's 25 times 10 to the negative 6, so that's 25 microcoulombs. So that's the amount of charge stored on the capacitor after the switch has been closed for a long time. Question 16. So they give us this circuit diagram, and they say 4 resistors are connected to a 36 volt power supply as shown. The potential difference across the 10 ohm resistor over here is 4 volts. A student says that the potential difference across resistor R, they don't give us that resistance, they say it's 32 volts. Now the question is the student correct? Why or why not? So it turns out that you guys can read through these answer choices, but it turns out that there is 32 volts across there. And how do we know? Well, if we think about Kirchhoff's loop rules, if you make any loop in a circuit, whether it's a simple series circuit or parallel circuit or a complex circuit like this, where there's things in parallel and series or a combination, that if we start from the negative side of a battery, we just draw a loop, and let's draw a loop that contains both R and the 10 ohm resistor. So kind of follow that blue line. We're going to call that loop number 1. If we add up all the changes in electric potential, it goes up across the battery, down across resistor R, down across this 10 ohm resistor. We add all those up, the sum of the changes in electric potential must be 0. And so from here, on the negative side of a battery, we always define that as 0 volts. And the battery is going to increase voltage by, well, whatever the voltage of the battery is. So if it starts at 0, it's going to go up by 36 volts. Has to go down by some amount, and down by, well, they say 4 volts, and get back to 0. And so if you go down by 4 volts, like basically how much the voltage increases across the battery is the same as the sum of how much it changes across R and the 10 ohm. So if it changes by 4 volts across this one, it has to change across R by 32 volts. So the answer is yes. There is a loop that contains just R and the 10 ohm resistor that we drew in blue, and the potential difference across R plus across the 10 ohm resistor will equal the power supply EMF. Remember, EMF stands for electromotive force, and that's just another way of talking about an ideal voltage source. So think about EMF like voltage. Therefore, the potential difference across resistor R is 36 volts minus 4 volts, or 32 volts. Question 17 reads, two groups of students use the circuit shown above to measure the potential difference across and current through the same light bulb. So two groups of students use the same bulb and they measure the current through it using this ammeter. There's our light bulb, and the potential difference across it using our voltmeter. The results of the two groups' measurements are shown in the graphs. So here's the results of using different potential differences, what the current is going through that light bulb for group 1 and that for group 2. So some of it looks the same, some of it looks different. It says, what can the students correctly conclude about the ohmic behavior of the light bulb? Well, we have to remember, well, what does ohmic mean? Well, an ohmic resistor, or something that resists the flow of current through it, which is pretty much everything except ideal wires, right? Will have a linear relationship between the voltage across it and the current which flows through it. So that's just like how we define an ohmic circuit element. If you graph the voltage across it and the current through it, if you get a linear relationship, we'll call that an ohmic resistor or an ohmic circuit element. And that's whether you graph electric potential on the y-axis and current on the x-axis, or flip-flop it. You can put current on the y-axis and the electric potential on the x-axis. But if you get a linear relationship, we call that ohmic. So if we look at the results from group number 1, they graphed it over a larger electric potential difference. And you can see that in the beginning, it kind of looks linear, but then it starts to kind of look like a side opening parabola, starts to level off a little bit. And so that's not linear over the whole range of voltages that they tested. So group 1 would show that's not an ohmic light bulb. What about group 2? Well, the data they have shows that it's linear. So within the range they tested, they could say, hey, from 0 to 2 volts and 0 to, let's say 0.12 amps, it behaves like an ohmic resistor. So just based on the data that they have, right, only conclusions based on the data, Group 2 can conclude that the light bulb shows ohmic behavior within the range of values measured, and Group 1 can conclude that the light bulb is non-ohmic, or it's not ohmic, just based on the data that's collected. Question 18 says, in the circuit above, the current through the battery is 15 amps. So that's I1 right here. Which of the following correctly describes the currents I into and out of point P? So point P is going to be right there. So we have I1 flowing into point P, and we have I2, and well, technically it's I3 plus I4 flowing out of there. So current 1 is coming in, and we have some other current with current 2. Let's call it, well, that would be I3 plus I4 flowing out. Yeah, which describes what's actually going on. So in a parallel circuit, we just have to remember, this is kind of the quick shorthand way. With the same resistance, right, they're all 2 ohms, we'll have the same current flow through them. Right? Well, why would we expect that? Because in a parallel circuit, there's the same voltage drop across each of them. So if they have the same voltage drop across them, just think about Ohm's law, I equals delta V over R. If they have the same voltage drop across them because they're in parallel and the same resistance, the same current will flow through them, right? I2 equals I3 equals I4, like this. And all of that current, I2, I3, and I4, has to come from I1, because I1 is what's providing the current into this junction, and then I2, I3, and I4 are all going out. And so that must mean that all 3 of these currents are 1/3 the size of the total current coming in there, which is I1 right here. So it says the current going through the battery is 15 amps. So that's I1. I1 is 15 amps. And each of the other currents has to be 1/3 of that, or just 5 amps. So the answer is C. I1 is 15 amps. And I2, I3, and I4 are all the same, and they're equal to 1/3 of that, which is 5 amps. And the last question that we're going to discuss today is number 19. It says, in the circuit shown above, simply asks, what is the current in resistor R? So things in color are things that I've added. So the original circuit diagram was just everything in black. So it shows kind of a complicated circuit. There's 2 batteries, 2 resistors, but it could ask a lot of different things, but it's just asking what the current is through this resistor. So this is a Kirchhoff's junction rule question, kind of like this was a Kirchhoff's junction rule question. The current coming into a junction has to equal the current coming out of a junction. And it's asking about the current that's going through R, so we know it shows that there's 3 amps of current coming into this blue junction, right? So there's something coming into this junction, and there's 10 amps going here, and 4 amps coming down here. That must mean there's 6 amps of current flowing from the right, from the red junction this way. So we have 6 amps coming in from the left, 3 amps coming in from the right. What comes in must equal what goes out. So there's got to be 9 amps of current flowing out of that blue junction, which means there must be 9 amps of current flowing through resistor R.